This is 0. Oh, no, okay. This is total. Don't say 0. Similar kind of thing I am doing. This entire thing was CPIG. It was T29.5 to T.
This will be Cp by T, CPIG by T, integrated.
CPIG by T dt, right? That's all. Because pressure is also changing, no? See, advantage of this formula. Pressure is, if the pressure changes, in ideal case, that effect will not come here. Because we know that Hij equals to Hij T. But Sij equals to Sij Tp. Man, you have to have everything in your mind, otherwise you'll have a big problem. So, if you say CPIG by T dt, it is absolutely wrong. Minus of? Yes, minus R and P. Correct? Okay. So, you have S minus Sig Tp plus T 298.5 degree Kelvin T CPIG by T dt minus R ln P by 1 bar. Okay, so we have S minus SIGTP plus 25.46 ln T by 298.15 plus 1.519 10 to the power minus 2 P minus 298.15 minus 0.7151 to 10 to the power minus 5 by 2 P square minus 298.15 square plus 1.311 10 to the power minus 9 by 3 T cube minus 298.15 cube minus R ln T by 1 bar. This is your S formula. Because SIGTP, SIG T25 degree centigrade P equals to 1 bar equals to 0. If you assume some other thing, that will be actually added with the S formula. So an S minus SIGTP for the Peg-Robinson method, which is R ln mod Z minus B plus 1 by 2 2 dou A by dou P ln mod Z plus B into 1 plus root 2 by Z plus B into 1 minus root 2. So this will give you pressure enthalpy diagram and this will give you pressure entropy diagram. Okay, so the table A and table B, you had Z, B, H and now S. The same table, fix up T equals to minus 100 degree centigrade. Fix up T equals to 1 bar. Calculate Z, calculate B. PV diagram is solved, not solved. You are getting the branches. You have not got the saturation pressure. Okay. And then after that you calculate H, calculate S, store it in a file. MATLAB can plot it. So if you want to write an interactive in MATLAB, you can do that, and MATLAB will finally give you a beautiful diagram. So what diagram you will expect? Pressure volume diagram you know. Next is pressure enthalpy diagram, pH diagram. So after doing entire this business, one can obtain pressure enthalpy diagram, which is H kilojoule per mole, P bar pressure, this zone is like this zone. If you want, you can put dotted line for your benefit. This is your vapor liquid regime. So please remember the pH, not PV diagram. This pH diagram. One pressure is there, and then we can have so this is, you can say, T minus 183 degrees centigrade, T equals to minus 175 degrees centigrade, not this, this should be like this, T equals to, say, minus 125 degrees centigrade. And where this occurred? Saturation pressure, you already got it by trial and error. By trial and error, you already got it. These branches will be coming automatically from the value of Z. You keep that, put the Z value in the formula of H, you get either this one from this. And these two, this kind of thing to be obtained based on your iteration or the formula. And then finally, beyond that zone, so this is like T 50 degrees centigrade. This is like your T 0 degrees centigrade. This is your pH diagram. Pressure enthalpy diagram. Have you seen this picture earlier? You have not seen pressure enthalpy diagram. It is very common. You have seen, right? Pressure enthalpy diagram. Now you know how to draw it from mathematics. Earlier we was, even when I was a student, I was thinking that okay, they have got, might have got from experimental data. Now I know how to draw this diagram. This is a pressure enthalpy diagram. Okay? So this diagram is known as pressure enthalpy diagram. I think the steam table and all those things, if you look at these kind of diagrams, you can actually get. Next is TS diagram, which is used for the refrigeration cycle, I think. Temperature entropy diagram. Okay. So instead of drawing TS, we go for TS diagram, which is not here degree centigrade, is joule per mole per degree Kelvin. And we have, and we'll get and some like that. So it is P equals to 100 watt, P equals to 50 watt, and P equals to say 1 watt. This is something called Euler diagram or something. Yes or no? Enthalpy entropy. So this is like TS. This is also useful in the refrigeration cycle. You know that we should go like this, come back, and sometimes you have to go by this path if you have enthalpy. You can have input enthalpy here also. Different enthalpy you can do that. But this is actually useful. This is actually you have got directly by your own hand, by your own calculation. The Pink Robinson, in the Pink via the Pink Robinson. And note, I want to make you to note that because we have DADT term. So for Pink Robinson, I also did the calculation, which is minus 0.45724 R square PC square by PC kappa to square root of alpha T PC. Okay, and alpha is 1 plus kappa 1 minus square root of T by PC whole to the power minus R. Kappa is 0.37464 plus 1.5422 omega minus 0.26992 omega square. And omega value, omega formula actually already have given. So this is the way one can calculate OA by dou. Okay, this changed already. Okay. So that's the way one can calculate OA by dou, and one can calculate the entire stuff. Generally speaking, that this value we take 0 here. Even if you don't take 0, if you look at the idealistic value is very close to 0. So it is not a bad approximation to have 0 for this. If you look at, I think Sandler's book, you can follow this part. Sandler's book you will consult. Sandler keeps some small value. Even if you add the small value, diagram will not change much. Don't get affected. So this is the entire story about the drawing this kind of diagram of the pH diagram and the TS diagram. Any question? Any doubts? Any confusion? So you can actually appreciate better, you can actually understand better if you write MATLAB or quote unquote.
So if we assume oxygen to behave in any other real gases like SRK or RK, should we be getting the same type of
A different value, you make a different value. Actually it depends. Now the point is, question is coming, a good question. Which equation of state then you use? Some of your friends said, okay, I do Van der Waals equation of state, why I do suffer? I use SRK, why should I suffer? I use PR, I want to suffer. The point is, nobody use PR. They will all go for BD, job is done. Thing is that experimentalists will be there. We are all engineers. Some of our other friends will work in the lab. He is measuring pressure, volume, enthalpy, entropy, particular temperature, pressure. He will give you data. You just see that Van der Waals may not be matching perfectly with this experimental data. With experimental SRK may not be matching properly. Payne-Levinson will be matching properly. So that's the way Payne-Levinson will. Some data we can see Van der Waals is doing fine. It depends on molecular configuration. How the polarity of the molecule. So the real gas polarity matters. Attraction, repulsion, I showed long back. How the Van der Waals equation of state has been corrected based on the polarity of the molecules. For that purpose we have omega. How the role of omega is, that we don't know. Experimentalists will give the data. That's why we need experiments. If you compare, you can say, okay, Van der Waals is having a lot of deviation, Payne-Levinson SRK is not having much, so of course we'll be going for Payne-Levinson SRK. That's the topic of research. And this is the whole cloud of topic. If somebody wants to generate this kind of graph, okay, I want to have the mixture. For pure substance is available. I want to have different organic components mixture. I am getting the lot of pollutants from the atmosphere. Oxygen there, then ozone there. So many things are there. Which is the best equation of state to get this kind of diagram that will be obtained from the experimental and the theoretical. So experimental and theoretical can go parallelly, and one can do a good modeling versus experimental research for having the pH, TS, all sorts of diagram using the proper equation of state with a justification of the experimental. Right? So still these things are the topic of research. We can do whole lot of research on this thermodynamics. Okay, so next, the last part of the departure, I'll be talking about the law of corresponding states. We have discussed in the equation of state. So how to have departure based on the law of corresponding of states. So let's look at that part and see the law of corresponding states and departure. So we'll go for law of corresponding states and departure functions. So Z is a function TR, PR and omega, right? When you look at the complexity factor, I think we have derived long back when we say Z equals to Z at PR, we derived in the class Z plus 27 PR by 64 Z PR square into 1 minus PR by 8 Z TR equals to 1. And one of my friends gave me I think you have given me the Carnot's method coefficients. So from here, one can actually write Z cube plus alpha prime Z square plus beta prime Z plus gamma prime equals to 0. This we have done already. So now people can ask, why to have for particular material? We will go for the material invariant. Only one diagram would be sufficient for all those. Because instead of having PV diagram, we can have the complexity vector chart. Complexity vector chart, Z versus PR, different here. If we can draw that kind of complexity vector chart, then you can actually draw similar kind of enthalpy diagram and the entropy diagram. So if you do that, how the departure will be? So we have not discussed so far in terms of corresponding state the departure formula. So we have, for example, if we talk about enthalpy departure, which is HTP minus HIGTP, which is P goes to 0 to T, PT, V minus T, dou V by dou T at P. This is dou H by dou P at fixed T. Okay, dou H Ig by dou P is 0. So you have only one term, and dou H by dou P is nothing but V minus beta T, right? You should be having all this formula handy. Dou H by dou P at fixed T. If you don't know things, look at it your last one. Dou H by dou P at fixed T. How much it is? V minus beta T. Beta, you know that beta Pt or something. T dou V dou T. Okay. And we know that Pv equals to Z dot. Now we'll be doing compressivity factorize. Okay, Pv equals to Z dot. And what actually this formula actually I have given? This is called Van der Waals equation of state. This formula will be changed for SRK and Payne Robinson. So please note down here. This is very important. This is only for VDEOS. If you have SRK EOS and the Payne Robinson equation of state, that will be different. Right? When you have SRK and the Payne Robinson equation of state, that will be given, one can calculate. We can actually do the Laplace derivation. I will not ask Rahul. Maybe Rahul can give later on those calculations if we have time, but I am not asking. It may be another couple of weeks you can take and get with the entire set of the compressivity factor. So remember that this is the departure formula I will be using in terms of the corresponding state. So Pv equals to Z dot T, and from here one can calculate RT by T, and this Z is nothing but a function of PRT from your compressivity factor chart. Okay. So how to evaluate this? V minus T, dou V dou T at fixed P. Remember that if somebody is lost here, I write it again here. P equals to 0 to Pi dou H by dou P at P dt. And this is nothing but the formula is there V minus T beta V, and from there this. So why I am not taking dou H Ig? Because we know that H is only a function of temperature. With the pressure, the derivative will be 0. Okay, so V minus T dou V dou T at fixed P. V is what? RT by P Z hat PR. Right? Minus integral P tending to 0 to P. Sorry, so T dou V dou P, so you can directly do that. T RT by P Z hat PR minus RT square by P Z dou Z by dou T. Am I correct? Yes. When I say dou V dou T at fixed P, dou V dou T means two terms will be coming. Okay. Because this has the function, this has the function. Okay. Two terms will be coming. Yes. You can say if you want, you can say dou Z by dou T. correct? Because Tr is nothing but T by Tc. So this has the T function, this is a T function. Okay? So one term will be Rz at by P into dou T by dou T equals to 1. That's what, but it is multiplied by T. That's why it's called RT by T. Another term is T you take out, T R by P to dou Z by dou T. Another T is already there. So that's RT square. But if you do that, this cancel. So you have this term itself minus RT square by P dou Z by dou T at fixed P. So my departure formula is H minus Hij Tp should be minus P taking to 0 to P RT square by P dou Z by dou T P dP. This is not complete because this is the function of TR. It shows the function of T and P. So you have to express in terms of everything TR, otherwise you cannot get it. So if you write a formula like up to this, is not the correct formula, right? The function of TR. So what will be your final expression in terms of PR domain? In terms of PR domain. So because so far this is not material invariant. This is not material invariant. This is not. We need to have in terms of material invariant. That means we need to have minus PR equals to 0 TR to some PR. Then everything in terms of PR TR. What will be the final expression? That's what I'm asking. Departure formula. If you do the calculation, I'm giving you some time here. Maybe 1 or 2 minutes. If I give 1 or 2 minutes, what will be your formula? If I give 1 or 2 minutes here, what will be your formula? Remember that dou Z, dou T is not correct. It should be dou Z, dou TR, dou TR, dou T. And dou TR by dou T you know. TR is nothing but T by Tc. So dou TR by dou T you know that. What is that? Dou TR by dou T? What is that? Dou TR? 1 by Tc. So straightforward. I am not getting only, I am getting answer only doubt from Rahul. So like that you have to change. Similarly, like P is replaced by PRPC. Because PR is nothing but P by PC. So, and critical temperature, critical is known, critical temperature known for particular material. Critical temperature is known. What will you get finally? What will you get? Remember that this will be dPr here. This will be dPr. What will be the things? What will be the final formula for the enthalpy departure from the compressive vector chart? The compressive vector chart. What will be the enthalpy departure formula? This will be written as dou Z by dou TR, dou TR by dou T. This will be written as dou T by dou PR. dPr, very simple. Whatever you have done, I am just doing the same thing here. And this is written as PRPC. That's all. You can get final formula. What's the final formula? I have given everything here. That's the kindergarten level of teaching thermodynamics. So, what final form you can get? What final form you can get? Yes, sir.
R TR square DC.
R
TR square DC.
TR square by TR square should be outside the back integral. Don't say we can. It's dangerous.
Yes, sir. It's outside the integral.
Outside the integral. Okay. Then
Sir, integral is 1 by PR square.
I will put RTC minus RTC PR square by PR dou Z by dou TR minus RTC PR square by PR dou Z dou TR PR dPR. Agreeable? Yes or no? Yes or no? Any no's are there? Okay. Rahul, how to evaluate this integral? See, law of correspondence state will give a nice formula for departure. The point is, you have to evaluate the integral. How to evaluate this? This formula can be further reduced to HTP or H minus HIG TP by TC. We can have minus RTR square. You can even take it outside, no problem. As you said, I will take it outside because my temperature is constant for the departure. That's okay, but that won't solve your problem because these guys are there. These guys there. So it is PR equals to 0 to PR dou Z by 1 by PR. Sorry, PR. Question is how to evaluate this integral. TR square I am taking out. You may be mentally happy for some time, but the problem is not solved yet. Problem is not solved yet. How to evaluate this integral? How to evaluate this integral? You have the formula for Z cube plus alpha prime Z square plus beta prime Z plus gamma prime equals to 0. Okay? I don't know how can you get dou Z by dou TR from here. But if you look at complexity of the chart, Z versus PR, we can actually have Z versus TR also. So, dou Z by dou TR, you have to obtain, put it here, and you can actually do by numerical integration. What method you can do? By trapezoidal rule. If you are having more advanced, Simpson's 1/3 rule, but Simpson's 1/3 rule has some limitation. What is that? You need to have odd number of data points or even number of data points. If you have a odd number, I think 1/3, or even number is Simpson's 3/8. Both are equivalent. It can be proved mathematically. Or trapezoidal rule. Trapezoidal rule requires a lot of data. Simpson's rule requires less data. Why? For the same accuracy. Because Simpson's 1/3 rule will fit the quadratic curve. Trapezoidal will fit the linear curve. Linear means you need to have more data. Otherwise, you cannot have the linear variation for data is very far. Because the curvature and all those things can be. Because if you have this kind of data, if you have one data here, you put linear, lot of error. But if you do quadratic, you have another data, you can nicely fit quadratic. That's why you get less. Even here also, if you put linear, we can see so much of error. If you put quadratic, less. So for linear, you need to have less. That's what you can actually put linear. So that's the way the numerical integration can be done. So this can be obtained from numerical integration of by PR. So you can actually calculate if P dou Z by dou TR, PR, TPR, and this entire thing you can do by numerical integration. Okay, this entire thing can be done by So that's the topic of research. People have done it. My art is to that. Again, if you can write computer program, how to do the numerical integration and get the correct departure function. It's a very compact formula. Earlier formula is very rigorous. If you have the proper equation of state, then you can have this z, and from this place, how you can calculate dou z by dou tr. In fact, what is the value of what is alpha prime? Do you remember alpha prime, beta prime, and gamma prime? It should be in terms of tr. Just check it out. We have done it. I think madam has done already. Madam gave me the paper, but this paper is not with me. Alpha prime, beta prime, gamma prime. Rahul, you may have also have. Right? Pardon? Alpha prime is there? Yes, sir. Okay, so that means it is possible to have dou z by dou t expression from here, right? It is possible. Point is, if you take dou z by dou t, it will actually what you have? It will have 3z square dz by dtr. Am I correct? If you take derivative, then alpha prime. So you will have very complicated expression of dou z by dou t. Very complicated equation. And that if you put it here, you cannot solve analytically. You have to solve numerically only. That's why I am saying numerically. First of all, you have to get it. So it will give actually, if you do it here, it will be like that. D alpha prime dtr z square plus alpha prime z dz prime, there dou z dou tr. And like that it will go. You have to calculate dou z by dou tr. See, point is everywhere you need dou z by dou tr, all the term except this term. So you without dou z by dou tr term, you take right hand side. Dou z dou tr will be left hand side. You take the other terms common, put it there. So it will have a very complicated term. So let's look at, since you erased it, maybe my friend can do it. Not now, several weeks. Okay, would have put this thing. You get a lot of motivation towards thermodynamics. So a lot of math is there in thermodynamics. That's why I get always excited. Z cube plus alpha prime z square plus beta prime z plus gamma prime equals to 0, which is 3z square dz by dtr plus d alpha prime dtr z square plus alpha prime 2z dz by dtr plus d beta prime dtr z plus beta prime dz dtr plus d gamma prime dtr equals to 0. Am I correct? What will you get then dz dtr? It is minus d gamma prime by dtr plus minus d alpha prime dtr z square minus d beta prime by dtr z. Am I correct? Numerator? Yes or no? Yes. Rahul? Numerator is correct or wrong? Numerator is correct? Divided by 3z square plus 2 alpha prime 2 alpha prime z, right? Plus can you solve analytically if you put it? So now your integral is 1 by PR. You write this expression minus d gamma, this will be dtr, right? Please correct me. D gamma prime dtr minus d alpha prime dtr z square minus d beta prime dtr z by 3z square plus 2 alpha prime z plus beta prime into dtr. Alpha prime is what? Can you tell me the alpha prime? You can put alpha prime, beta prime, gamma prime. I just want to show how complex it is. Minus
64/5
PR. Okay, PR is there. Alpha prime. So this alpha prime PR, this is 0 or not? In DTR, it is not 0. So it has PR. Gamma prime has PR. Yes. Beta prime has PR.
Yes, sir.
Yeah. So it cannot be 0. Very complicated function. If you want to do closed form analytical solution, integration not possible. Even Van der Waals, Bain-Robinson are all much complicated. Okay. So one can get H minus HIGTP. So you got the idea how to get it. I will show you that the corresponding state, how to calculate, how to get this all this diagram, this enthalpy diagram and porosity. So this is clear. So now this is very clear because this equation is known to us. You can directly get this derivative and calculate the integral by numeric integration in MATLAB or Fortran, and you can get this H minus HIGTP by TC, and we can assume HIG of oxygen is 25 degrees centigrade, 1 bar pressure is 0, and you can get H, and you can get whole lot of data. This is the one. Similarly, one can have entropy departure S minus SIG TP, which is minus R, PR equals to 0 to PR, Z minus 1 by PR plus PR by PR, dou Z by dou TR, PR dPR. Prove it. I am not proving in the class. You can prove it at home. Okay. In the exam, what I may ask you to do that? I may ask you to do that. Okay, obtain the compulsory factor equation, cubic equation for Bain-Robinson. I will ask you to get this type of formula, final formula for the departure for enthalpy or entropy. That my friend will be giving me in a couple of weeks before the second quiz. So this is the entropy formula, and then you can again use it and calculate the entropy. So I will give one such diagram in a reduced corresponding state, and let's see how it looks like. H minus HIG minus H by TC, because negative sign is there, that's why I am putting HIG minus H, calorie per mole per degree Kelvin, which is PR. This is saturated liquid, and this is saturated vapor. So this is TR1, this is TR2, this is TR5, different diagrams, and then finally you get. So this is the diagram you get from this whole lot of exercise. So this kind of diagram is there in the books. Again, we don't look at this diagram. We just go to the next page because we are not interested. I think we might have got with some experimental data. Who wants this diagram? And no exam will ask. But now we know that all these thermodynamic diagrams, tables, you can prove mathematically. Because the people like us, me, who don't know, who don't want to do experiment, who don't know how to do experiment, for us it is important to have this kind of diagram. So that completes the departure formula. I think we have done a whole lot of analysis of thermodynamic departure. Some of you for the first time in life in thermodynamics course, and we have also learned what are the applications. So now you can see that departure application is every corner in our life. Calculation of enthalpy, tables, the behavior, phase change behavior, everywhere we can actually have thermodynamic departures. So next we will be slowly moving. We have talked lots on the liquid and vapor. We talked about this liquid and vapor equilibrium. Vapor liquid, we say equilibrium. What does it mean? What does it mean by thermodynamic equilibrium? So let's start. I will just give very brief, within 5 minutes I'll leave you. So just to say what is thermodynamic equilibrium. So thermodynamic equilibrium. This duster is here, it is equilibrium. If I put it like this duster will go at the top, at the bottom, different equilibrium. For example, if I put a ball here, ball comes, sometimes ball will come here, do the simple harmonic motion and rest at one place. Why rest? Potential energy is minimum. That's why it will be rest. And we call minimization of energy density. We call minimization of energy density. In thermodynamics, where we don't care much on kinetic energy and potential energy, we care on internal energy. In thermodynamics, we care on internal energy. Thermodynamics, we care on internal energy. And we say that internal energy has to be minimized. Right? We don't have kinetic and potential energy impact. If we have, of course, we have to consider all that. So in that case, total energy means kinetic energy, potential energy, internal energy. But here we have only internal energy because we don't care for kinetic energy and potential energy. So when we talk about minima, we again go to mathematics. Minimization of functions. When I say function fx has minima or has maxima, you always go and check something first. Which you go and check? Derivative is 0 or not. F prime x equal to 0 or not. Why we check? Because if you do this type of diagram, this has local maxima, this has local minima, local maxima, local minimum. And if you draw the tangent, you can see that f prime x equals to 0. Okay, so that's what. This is the first criteria to have minima or maxima. This is the first criteria to have the minima or maxima. Second criteria is why this will have maxima, why this will have minima. So then we go by Taylor series. We go by Taylor series. So if I say x equals to x star as optimum, optimum denotes minimum or maximum, what you want. Then we can actually write Taylor series fx equals to fx star plus x minus x star f prime x star plus x minus x star whole square by 2 factorial f double prime x star and higher order Taylor series. When it has optimum, f prime x star equals to 0. Okay, optimum means at this point x equals to x star. I am talking about this one. That means at the optimal situation, at optimum, fx minus fx star will be x minus x star whole square by 2 factorial f double prime x star and not considering higher order terms. And when x star is a maximum, fx is less than fx star. Any x we consider fx star is maximum, larger, right? So in that case, what will actually happen? This is negative. So the double derivative has to be negative. This is square term. So that's why for a maximum, second derivative is having negative sign. Similarly for the minimum, second derivative is maximum. But that is not the case for thermodynamics because this guy is the function of S, B, N, 3 independent variables. There is only one independent variable. So in the next class, we will discuss the multiple variables, how to do maximum, minimum, and proceed further. Thanks for kind attention.